In the previous section, we have discussed the general form of the traveling wave in one dimension. Now, in this section, we will discuss a special form of the traveling wave that we use frequently in the topic of wave motion, that is the sinusoidal wave. The sinusoidal wave is a traveling wave that the functional form of the wave is the sinusoidal function. Sinusoidal function. So, if we take a snapshot of the sinusoidal wave, we will have the curve like this. Okay. In this curve, the brown curve represents the snapshot at the time t equal to 0, and the blue curve represents the snapshot at the later time t. And you can see that the wave moves with the distance vt, where v is the velocity of the wave. So if we look at the same displacement, like at this point, it will move the distance vt when the time pass from t equal to 0 to t. So this is a traveling sinusoidal wave. The mathematical form of the sinusoidal wave can be written as the y xt is equal to a sine x minus vt for this wave that moves to the positive direction. So we have the general form of the wave function is something like this. You can see that we can compare this with the wave function that we have discussed in the last section. And now the functional form here is a sinusoidal function, which is the a sine. So we can write the displacement at the point x and the time t of the wave is a sine x minus vt. However, this form of the traveling sinusoidal wave is not the form that we usually use in physics. We can write the functional form of the traveling wave in a little bit different way as a sine kx minus omega t. Here a, k, and omega is are the constant. And we will see what is the physical meaning of these t parameters. The most obvious parameter is the parameter a, this parameter. Since the sinusoidal function has a maximum value of +1 and a minimum value of -1. So you can see that A is the maximum displacement of the wave. A is the maximum displacement of the wave, and as we have discussed in the oscillatory motion, we call this parameter as the amplitude, but now it is the amplitude of the wave. And if we look at this diagram, the amplitude is the maximum displacement here, A, and also the minus A is the minimum displacement of the wave too. Now, if we take a snapshot of the traveling wave at time t, it means that if we fix the time t in the wave function, if we fix the time t, so we can say that y is a function of x at a fixed value of t is equal to a sine kx minus omega t. Again, we consider the wave that move to the positive x direction, but in this equation we fix the value of t. This value of t is fixed, so it is just a constant in the function. And if you plot the value of y as a function of x, you will get this kind of curve, the sinusoidal curve. Okay, and if you look at this figure, you can see that this figure is the snapshot of this sinusoidal wave at the time t equal to 0. Right? Because we can see that at x equal to 0, y is equal to 0. So we have to put t equal to 0 here, but that is not necessary. We can do the following analysis without taking the t equal to 0 here, but t is fixed. Okay, so this is a snapshot of the wave at the fixed value of t. We can see that the curve repeats itself at a certain distance lambda here. Okay, if you start at this point and follow the curve, it will come back to the same displacement, and this distance we call it lambda. Okay, we call this lambda. So since we know that the sinusoidal function has a period of 2 pi, so we must have that the displacement at the point y x t is equal to the displacement at y x plus lambda t. This value of t, remember that this value of t is fixed, and from this, on the right side of the equation, we have this equal to a sine k x plus lambda minus omega t. Okay, or we have that a psi kx plus k lambda minus omega t. And since the displacement repeat itself when x shift from x to x plus lambda, but we know that the sinusoidal function has the period of 2 pi, so it means that this value of k lambda is must equal to 2 pi, or we have that k lambda is equal to 2 pi, or k is equal to 2 pi over lambda. So this is a physical meaning of the constant k. It is the reciprocal of the lambda times 2 pi. We call this the wave number. We call k as the wave number. K is called the wave number because if you look at the relation of k with the lambda, the reciprocal of lambda will give us the number of waves in a unit length, right? Lambda is the length of one cycle of the wave. You can see that if you go one cycle like this, and the distance from this point, the starting point, to the end point, that when it repeats itself, is the lambda. So the lambda is the distance of one cycle of the wave. The reciprocal of lambda is the number of cycles of the wave in a unit length. So that's why we call it the wave number, because it gives the number of waves in one unit length. Okay, so now we have the physical meaning of k.